All right, so I'm about to do my module on my presentation on module 3. I've never used this before, so please bear with me. All right. There we go. Okay, so I use SPSS, and obviously it's not that great as far as the graphing component, but it did give me a complementary table, so I'll present the same information, but it won't be as pretty. So MRC, multiple regression and correlation, it's test of association. Have a nice little standard formula, y equals b naught plus bx. So basically, expected equals predicted plus error, which is the residual. And so this is a line of best fit and gives us smallest least squares. So basically, in relation to that line, the residuals are going to be close as possible, indicating that zero. It tells us how multiple independent variables impact the criterion, aka outcome variable, and error is attributed to the model. So I chose to use y1 and then x1 through x3 for my independent variables. So here are some descriptive statistics, but what we really care about is down here. So these unstandardized b's are going to be, so this is right here is your intercept, which is the constant, and then these are the slopes or the weights for those independent variables. The standard error, you want that to be as small as possible so that there's less variation of around these, so that we have like a more solid best guess for our data. So for this test, the null hypothesis is that these b's are equal to 0. So then when we look at the t's and significance, aka p-values, we see that none are lower than none are significant. So we can say that none of these values, we fail to reject the null hypothesis that b equals 0. So it's important to note that t and p are inversely related. So these relatively low t values result in these high significance values. All right. Yeah, just to reiterate, the b's are slope, so how much a change of one in the independent variable change the dependent variable. All right, so now the assumptions that we want to try not to violate for the MRC. So 1 and 2 are pretty self-explanatory, so right there. So now we get into the ones where we actually need to test for. So independence of residuals. So for SPSS, it gave me the Durbin-Watson test, and that basically says, if the value is 2 or close to 2, then we can safely assume that we did not violate the independence of residuals assumption. And so I don't have reason to believe that I violated that. So we're gonna look at 4. This looks at the linear relationships between the residuals and dependent variables. So we got residuals right here, and then predicted, the unstandardized predicted. So it, like I was saying, R would have been nicer as far as the graphs because it's consolidated, but this is an overall relationship. It seems pretty good, but I would be weary about maybe these right here and then these two values because they might be linearly, or they seem like they're related, which we don't want. So then we look at the partial correlations, and individually you can see that they're slightly problematic in all of them, which lead to the nature of this one. So assumption 4 may have been violated. Homoscedasticity of the residuals, basically looking at the variance around the regression, making sure it's the same for all the predictor variables. Once again, I'll say that this data right here is problematic and maybe that point. So assumption 5 may have been violated. This is a really, really important one. So basically, collinearity is bad because we don't want our independent variables to be related. And so if we look at x1 and x3, right here, that's a pretty significant correlation. But that might be due to the fact that we have so many variables, like as you add more variables, there inevitably will be a relation among some of them. So to further verify that I did not violate this assumption, we looked at the variance inflation factor, and the rule of thumb is that variance inflation factor around 1 is acceptable. And when you get closer to like 5 or like 10, that's when you really, need to start looking at your data. So I don't have reason to believe that I violated that assumption. Seventh is outliers and leverage and influential points. So it gave me the Cook's distance and the center leverage. This is minimum, this is maximum. Obviously, a max of 0.9 is very close to a 1, which is deemed, significant for this test. So that's a red flag. But then when you look at the averages, the average for the Cooks is only 0.063. So overall, the data is good. There aren't any points like pulling it or, weighing it down or anything. So that 1 point is problematic and would be a red flag. The eighth and final assumption is that the residuals are normally distributed. So SPSS actually did me a favor and gave me this nice little curve, and you can see that, it's fairly close to being normal. If that was right here, that would be perfect, but I'll take what I can get. And then they follow up with this nice line. You can see everything hugs, about the same above and below. So I don't have reason to believe that that was violated. So what does all this mean? So let's start. So we get this equation right here based on the values that we had in the unstandardized B column. So this R squared value is of importance because it tells us the proportion of variation in the dependent variable that can be explained by the independent variable. That's what we really want to look at. We're using these models so that we can make predictions. This model is a parameter estimate because, we don't care about necessarily the statistics that we got from the sample. We're trying to use that information to, make inferences about the population. And so we really would like for this R squared to be a little bit higher so that we can, know that when we change an independent variable, the dependent variable will respond in a predictable manner, because we use this stuff for like medicine and important things that can impact people's lives. So also Gary King stressed that we need to analyze all of these independent factors to get the variables together so that we really understand how the dependent variable act or will respond, because in most cases we can't really like tease these different independent variables apart. So if we try to analyze one dependent variable or one independent variable with the independent variable and like combine it, we like inflate the betas and the standard error, which is just all bad. So that's important to keep in mind. So next we're going to go to ANOVA, which is the second branch of the general linear model. It's measuring the difference between means. It's basically just a ratio of signal to noise, sum of squares over degrees of freedom. But in this one, the error is attributed to the user because ANOVA is classy. Differences, MRC is association, ANOVA differences. But it's neat because we can switch between the two with statistical computations using the point by serial formula. Like I said, ANOVA is more strict, but essentially they both compare the influence of multiple independent variables on a dependent variable. So data, I try to get cool and use political affiliation for F4 and race for F5. And then the dependent variables income, so those numbers aren't important. So main effects and interactions. So for this test, the null hypothesis is that the difference between the means for the different categories or cells is 0. And so we look at this F statistic to guide us. And so F is just signal over noise once again, or variance between groups over variance within. And as we can see, none of these are significant. So none of the independent factors, or there was no main effects or interaction, which didn't surprise me based on the data. So that's why I chose to leave the type 3 sum of squares, because I wasn't gonna have to tease out like any overlapping data, which also led the lack of significant results led to me not having to do it post hoc, because I didn't have to go back and see what was causing the significant interactions or significant test result for the F. And then this is just showing you that, confidence intervals for the 4 categories, there's nothing special there. So assumptions again, 1 through 3. So, these are self-explanatory. I'm going to go over them. So residuals and outliers. Once again, SPSS didn't do me any favors as far as the graphs, but for obviously it produced a plot for each different combination of variables. So this is the only one that produced an outlier, which is participant 6, and it's a point outlier, which we talked about in the Cortina article. So yeah, that's problematic. And then so for normal distribution of residuals, it gave me the Shapiro-Wilk statistic, and basically that one is, the way that's set up is the null hypothesis is that the values are normally distributed. So the null is that. So we failed to reject the null hypothesis. So basically what we're saying is, these values are normal. There's no reason for us to believe that they stray from being normal. So assumption 5 was not violated. And then this is just a visual for all the different scenarios. So you can see how we get lines. Once again, R probably would have been useful just combining those and producing one line, but same information. The last assumption is homogeneity of variances. So basically what I was looking at is making sure or it says right here, test the null hypothesis that the error variance of the dependent variables equal across groups. So it's not, you don't want one section of the graph to have like high variances for the high variance for the residuals, and one graph or one section have low. So that's just how we look at that. And so we get another F statistic. And so the degrees of freedom, we have 4 groups or 4 cells, and then 30 individuals total, because we had a nice balance design, 15 and 15. But ultimately, we failed to reject the null hypothesis, so we can say that there was homogeneity of variances. So we did not violate assumption 6. So what does all this mean? Basically, for my premises rate, or for my study, race and politics had no effect on income or impact on income. So overall, we use ANOVA to test the differences of the means for different treatment groups. And it's important, again, because our estimates equal the population parameters, and just to beat it in the ground one more time, the population parameters are what we really, really need to be careful about, because we're going to use those to, make important decisions that impact others. And, these are tools, but they can't compensate for a bad design. So we need to effectively use these tools to, broaden our knowledge and make a good impact on the scientific discoveries. And that is it.